All right, welcome back, everyone. In this video, we're going to look at two different things. It's titled axial loading, which is really what we're after, meaning as I am in tension or compression, we're going to look at the overall deformation. We've already talked about strain and it's related to that, but it's kind of combining some principles we've had so far. Before we get there, I want to touch on one little principle, and that's St. Venant's principle. And the idea is really about stress concentration. So the idea is if I have this cylinder that I see here, let me turn on my, let's actually draw on this thing. If I have this cylinder here and I have it in compression, this square rectangular cylinder, and I were to say, cut it right here. Well, we've already said what's going on internally. And we said internally, what we have is this stress that's pushing up, right? And what we said before is it's linear. It's the same throughout, evenly distributed throughout the cross section. But is that really true? So what would be the difference if I cut it way up top? There's no plate or anything like that. This is like a point load versus down here somewhere, right? And that's really what St. Venant's principle is about, is how that stress changes throughout the depth. And this is a cool little foam example of what's going on here, where I have these horizontal lines represent stress. So the closer they are, the higher point of stress. And we have this device and we push down on it. And what we see is these lines get very close together, right? And they're getting very close together right at that point. And eventually, if we move far enough down, the lines once again are the same as I move vertically, right? So what we have here is a stress concentration. Those distance between lines get closer, and that's where it'd be most likely to fail. But the question is, or what we can look at with St. Venant's is, how far do we have to move away from this load before these lines are all parallel and equal distance apart, right? Because we can see the further away I get, the more that happens. And the principle basically is we can look at, well, basic rule of thumb is one diameter of major of width of the major width before we get to that average. Here we see an example, an illustration of how that would work, where as I'm this distance down, I see the stress concentration. It's definitely higher in the middle or where that load is being applied than further out. And if we think about what it means when it says major width, well, there's two really widths here. There's this one and there's that one. Well, the major one would be this bigger one. So if that's how far I go down, right? If this is the same as that, that's when suddenly it becomes the average. So it's just a principle, no mathematical calculations here, just an idea of getting away from those stress concentrations and moving away from the point of contact. All right, let's move on to the point of the topic today, this idea of axial loading. And we're going to develop an expression that will help us figure out how much we get deformation. How much is the length changing if I put this in tension, right? So we have, let me go down here and now click on my highlighter. We do have a length and a change in length. We've talked about that as being strain, right? Which we have this epsilon is equal to the change in length over the original length. We called that strain. We've seen this before. We've used it before. Well, one way I can rewrite this in this derivation is I can say, in essence, strain is equal to the rate of change of the length with respect to the x direction in this case. Or what that means is d delta dx, right? That's what I see what I'm writing over here. Well, I'm going to rearrange that equation and solve for d delta. And I have d delta is equal to the strain dx, right? Well, I know this relationship between stress and strain with this modulus of elasticity is stress over strain. So I'm going to rearrange that to say that strain is equal to the stress over the modulus elasticity. Basically, what I'm trying to do is take this equation and instead of strain, I want stress in there. So that's really what I was doing. So I get that. And I end up with d delta is the stress over the modulus elasticity dx. Well, I also know that stress is force, or P over area, right? Force over area. So I can sub that guy in to get my my final look where it says d delta is equal to p over AE dx. So this p over a is what we subbed in for that sigma right there, right? And then I can integrate, and what I end up with is a total delta is equal to the integral over the length of p over AE dx. So that's the equation that we derived. Let's take a look at an example in action. What we have is a round stepped shaft that's made out of steel and a yellow brass, bonded together in some way. I'm pulling it with 1,000 pounds or 1 kip load. Two lengths, a 10-inch for the steel, 15-inch for the yellow brass, two diameters, one for the steel 2-inch diameter, yellow brass 1 inch. I know the diameters because it says it's round up here, right? So what do we want to find is, what is this total deflection at C? Meaning, if I were to pull on this system, the steel is going to get longer, the yellow brass is going to get longer, and together we're going to have a total change in length over here at point C, and that's what we're trying to find. Now, on a problem like this, a lot of times the E won't be given. The modulus elasticity or Young's modulus, which we need for this equation, is not given. Everything else we can find. P, if I do statics and cut it right here and sum the forces in the X, the force is 1 kip. If I cut along here through the steel, the force is 1 kip. So no matter where I cut it, the axial force is 1 kip. But E, I do need to look up sometimes. If you do need to look it up, there's tables out there. Where I'm pulling from, this is out of the Beer textbook, Mechanics and Materials textbook. And I can just scroll down and what do I see? I see yellow brass is one of the materials. Oh, I can't write on this. Always fun. I guess I could if I do this. Let's go draw this. And if I said yellow brass and I scroll over and I say, what is the modulus of elasticity, which is right. Oh, no, I can't write. Oh, whatever. Modulus elasticity, which is in this column. Hopefully you can see it. Well, I'll try and draw one more time. Nope, still nothing. All right. Regardless, modulus elasticity set. Now I do notice it says times 10 to the 6th PSI on this column heading. However, what we're doing is KSI, so it'd be times 10 to the 3rd if I did that conversion. And for this this yellow brass, now it's not. Oh, now it's letting me move. Well, maybe not. Okay, I'm blowing this whole thing up. For this yellow brass, I see that value is, oh, why you highlight? Okay, this whole thing's a nightmare, but I see the yellow brass is like 15. But that's where you'd get it if it wasn't given. Steel is 29 times 10 to the 3rd. We've used that quite a bit already. So let's go back to this total deflection equation. We said deflection is equal to the integral over the length. Well, this whole thing is 25 inches long. And then we have our P over AE dx. So that's the same equation we just have up above. And what I can do is break this into two different segments. So from the 0 to 10, like I said, it's 1 kip on both segments. We have the 1 kip load. The area, we said area is way easier to find when you're given diameters using pi over 4. The diameter is 2-inch squared. I'm going to drop my units because it's getting a little tight in here. E, I looked that up, or I have it given as 29 times 10 to the 3rd if we're in KSI, right? Don't forget my little dx here. Plus, for that second segment going from 10 inches up to 25 inches, I have that same 1 kip load. Because if I sum the forces in the X, it's constant throughout. A different diameter here of 1-inch squared. And then I have the 15 times 10 to the 3rd, right? KSI dx. Well, when I integrate that, we're integrating with respect to X. Well, nothing changes with respect to X, meaning as I'm moving in this X direction either way, this P value doesn't change. It's the same. The area is the same. E is always going to be the same unless the material's changing or something weird. We can break that apart the way I did here. So when I actually integrate this thing, I just end up with just X, right? So this would just become X over all of that. I'm not going to show that derivation because it is so simple. And then I evaluate it from 0 to 10. I'm going to pull out that 1 kip. So I'm going to skip a couple steps here. Hopefully that's not too hard for you. And I'm going to plug in that 10 for X. So I have 10 minus 0 for my limits. And then on the bottom in the numerator, if I plugged all that in right, I end up with 91,106. And these would be kips. And of course, these are inches, something like that, right? I think I did that right. And then for my other one, plus I have that one kip load. I was going to pull it out of both, but I forgot. Whatever. And then I have 25 inches minus 10 inches for those limits of integration, divided by, if I do pi over 4, 1 squared times 15 times 10 to the third, I ended up with 11,780 kips. Cool. So then if I went ahead and did my algebra correctly, I end up 0.00011 inches for how much the steel elongates, and then the brass 0.0013. Of course, brass is going to elongate much longer because it is a softer material, so we'd expect that. It's also narrower, which would make it expand more. But we end up with 0.00138 when I add those together. So that would be my total deflection at point C. Now, what we notice here is that the integration was trivial, right? I mean, why even talk about integration? And really, the only reason we have to include integration is if that p-value, that force is changing, the area is changing. That's the only way. But 99% of the time, that is not the case. And because it isn't 99% of the time, what we typically do is we say, well, let's say if we do have a constant load in area and I have these multiple segments, what I can do is I just add up PL over AE, right? So that's much quicker, much easier. I go right in for if I were to redo this problem, my P is 1, my L is 10 and 15, my A I just found, and my E values I can look up, right? So I just add those two up, nice and easy. Cool. Let's look at it one more example then with this concept. What I have is an aluminum shaft. This is kind of a hard one to see, maybe not. I did draw this section to maybe hopefully make it a little easier, but I have this aluminum shaft and I have a steel rod, and this is like a section right through the shaft, right? So I'm pulling on this steel rod with 80 kilonewtons, and what I want to find is the total deflection at point C. So what's going on here is the steel rod here, this is steel rod all along here is under tension. It's getting pulled, so it's going to be pulled to the right as it elongates. And we already know now we can use this PL over AE. Well, what do we know about this aluminum shaft? The aluminum shaft is under compression, but it's also, as it compresses, it's also moving. So we have, let me do this. So we could do delta of the steel, right? Steel plus we have the delta of the aluminum. They're both causing it to go to the right with this 80 kilonewton load. So we're going to add these two together. So let's break it into two different parts, starting with the aluminum. With this aluminum, we just said that delta is PL over AE. This is as easy as just plugging it in. And for the force on the aluminum, similar to the last problem, what is the total force? Well, we have that 80 kilonewton load, but we want to be in newtons. Don't forget that. So we have 80,000 newtons. What about a length? Well, we see the length of the aluminum is this 400. It's just the length of that shaft. So we have 400 millimeters divided by the area. And I was nice to you. I gave you the area instead of, if you had to find it, of course, you could just do the, the pi over 4 d to the pi over 4 d squared of the outside minus pi over 4 d, or actually pi over 4 parentheses d outside squared minus d inside squared. I don't know. You can figure it out, right? Just area. So, but I give it to you as 400 millimeters squared. Of course, you'd have to know the wall thickness. I didn't give that, but regardless, what do I do about E of aluminum? Well, I go back to that table, and I'm not going to go there since it was such a nightmare last time. And I look it up, and I found it to be 70 times 10 to the third megapascals, something like that guy. If I plug all that in, I ended up with 1.143 millimeters. And of course, it's moving to the right. And then steel, same idea. With steel, I have delta steel is PL over AE. The only difference is for the area steel and E of the steel, but the P is going to be the same, right? Because I have the same 80 kilonewton load pulling on that steel. Length of the steel is a little longer because it extends beyond that little bit, and I see that it is 600 millimeters long divided by area of the steel. That one, do I give that? I do give that one. Wow. Instead of giving diameter. So area of steel is 78.54 millimeters squared. And then E of the steel, I look that up to be 200 times 10 to the third, or you just memorize it because we use it so darn much. And with that, I ended up with 3.056 millimeters. And like I said, since they are both pulling it to the right, I'm going to add those together. So delta at C will be equal to my delta of the aluminum plus my delta of the steel, or 1.143 plus that 3.056, giving me a total of 4.20 millimeters for a total deflection at point C, assuming I did everything right. So in essence, what this does is if before we learn about this PL over AE, what we could have done is we would have said, well, we could find our stress is P over A for each material. From that, we could find our strain because we know a relationship between our stress and our strain from a modulus elasticity. So and then from that, I could find my strain, and then from strain, I could find my delta is equal to the strain times the initial length, right? So basically what this does is it allows us to take all these principles and instead just go right in and say delta is equal to PL over AE, right? So just a much easier, simpler way instead of doing all those steps. So hopefully you found that interesting. Thanks for tuning in, and I'll see y'all next time. Thanks.